Oh, I didn't upload the notebook from last time. Okay. Hey, good afternoon, guys. So, a quick announcement. I created the spreadsheets for projects and possible additional topics on in the announcements. So, yeah, you can think about projects. So, today is we will finish the topic on retrieval, uh, which we will cover in homeworks. So we will have the last homework 10 on the this week topic for retrieval. And as you remember, if your project will be on one of these topics, you you can skip this homework and just do the project on retrieval or fine tuning, whatever project you choose. Okay, let's see. Yeah, I have this notebook opened from last. Oh, and I didn't upload the homework. Okay. Um, so last time we talked about HNSW algorithm for the fast search. Let's see. Mhm. Let me import NumPy, install face. And as you remember, um, the approximate search with, so we did two searches, one with L2 distance and another with hierarchical navigable small world graph. And even with one level of hierarchy, it works very fast. But the fast doesn't mean accurate. So let's look at the uh, performance of these algorithms. But before we see, yeah, let me create the index because it takes some time. Okay. And then we created this index. Okay. Bless you. Um, nee. Okay, I made a misprint. Neighbors, neighbors. Okay, so yeah, let it run. Uh, so did you hear about MongoDB databases? So do you know that they use Faiz under the hood? So for the search. Um, okay, it's running. As you remember, in this algorithm, hierarchical navigable small world, they built a graph with given number of neighbors, but then they also add some additional edges to I don't know, random uh, points, or there is some strategy to get to like more distant uh, nodes of your graph. And after that, um, there is a parameter. So index has a parameter h and efficient. What's wrong with projector? Efficient construction. Um, and efficient search. Let's use both. Index efficient search. So efficient search parameter by default is 16. It creates the heap data structure and limits your search by the closest, in this case, 16 neighbors. It Oh, so do you remember another algorithm which also limits our choice by some number of uh, options? For we use this in sampling when we uh, so assume we build the graph and now we want to find the neighbors uh, for um, for one vector um, and instead of um, searching through all neighbors. I don't know, for example, if we indicate the number of neighbors 60, uh, we will limit our search by a small amount of the best neighbors, like 16 by default. Do you remember another algorithm which limits our search on every step? It's called beam search. Beam search. So it looks like those guys 10 years ago didn't know the name of beam search, so they called this efficient search, but it's the same as beam search. Uh, so F search stands for efficient search. When we uh, instead of performing grid search, limit our ourselves by some number of best closest neighbors. Okay, it's still running. Okay, while it's running, I want to write a small code to compare the neighbors that were found by Well, by exact algorithm and by the approximate algorithm. And we will see how accurate is this approximate search. Um, so let's write. Uh, let's create a variable reference as and p, let's say zeros. Um, of size of query. And you remember we were searching for 10 neighbors. I will take the top one, the nearest, the closest vector for to compare the accuracy. But okay, so for every vector in query, I will just store the index of the closest vector from our data. Query dtype for I in range query, index search, and index will find the distances and the indices. So distance and best index and okay, yep. Reference I will assign the best index. Oh, it's finished. Okay, let's create this array. And let's do the same for approximate search. Yeah, so by default, this parameter is 16 and this parameter 40 for the limit of best neighbors for construction and for search. Reference and approximate. Approximate, then of query, index 2. Index 2 and approximate. Now let's compare the accuracy between reference and approximate. And the accuracy is 20%. So fast doesn't mean accurate. So let's change some parameters. For example, when we perform search, let's use more data, let's say 30, and see how the accuracy is changed. Oh, the accuracy now is 30%. So if we use for search the heap size 60, then the accuracy now is a little bit less than 50%. So yeah, as you can see, the the uh, majority of time is used on the construction step. And in construction step, we can also use larger size of heap. And we also can consider more neighbors to make our predictions more accurate. So for example, we can use larger number of neighbors, but of course it will take more time to build this graph. For example, let's use 64 and build this graph. Yeah. And then I'm sure the accuracy of this approximate search will be better. But I'm looking at the accuracy only of the top first result. As you remember, in retrieval task, it doesn't matter that our correct answer is the first answer. It can be one among top 10, for example, and large language model actually will still understand which answer to use, and it's fine that our search is not 100% accurate. I mean, that we have the best choice, that we don't have the correct answer in the first best choice. If it's in first 10 or 5, it's fine. Okay, while it's running, I want to show another code for DuckDuckGo, the agent that goes into internet for search. So so we import also Wikipedia because we will do search in Wikipedia. Then we will look at homework. At some point, it will ask me also for the token from Hugging Face, because without this token, it has limited number of access to this agent. And I created these tokens in my secrets. So first we will ask a large language model without access to internet. And here we use Quen about who is the last president of the United States. And it will provide the answer on the time when this model was trained. So now it's still uploading. Okay. Uh, okay. I okay. Um, oh, by the way, this in this notebook there is example how you can run this large language model on API, not on your machine. So you don't need to upload the weights. Uh, so here's example. Hugging Face API agent, and you upload on the tokenizer. Okay. And yeah, and here is the request, the typical request to the to chat model or instruct model. Uh, you can see we indicate the role, user, and then content. Uh, content. Let's run our model. And here is the answer. The last US president, as of my last update, as of my last update, so it speaks like a person, um, is Joe Biden. He was inaugurated in na, 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 na. If you're asking this question at later date, it's possible that there might be have been a change. Okay, so it provides pretty accurate answer, but it doesn't answer the question. Now we can use this transformers agents tool, DuckDuckGo, and and apply this agent. So we should give permission to this agent um, which data it can access. For example, math time requests the Python library for searching for web search, regular expressions, and Wikipedia. And let's run our agent. So this agent is written as a prompt. And in this prompt, it has some reasoning. And here is the output. In the output, you can see this reasoning. Agent thoughts. And here are the thoughts. I will use the tool Rob Search to find the latest US president. Then agent executing the code. um, here is the code. Um, then uh, this is the output from the code. Here is the source, Wikipedia. Um, then agent again thinks. um, Based on the search result, the latest president is Donald Trump, who won election in 2024. I will now answer the question with this final answer. And so we can see the reasoning of this um, agent. And finally, we have the answer from this model on our question, who is the latest president of the United States, Donald Trump, which is correct answer. So you can use search in your data set, in your documentation, or you can do the search on the verb. And then there is example how you can run this agent with model uploaded locally. Okay, the HNSW is still training. Okay, while it's training, we can open the homework and look at the homework. And again, I didn't upload the this notebook and homework. I will do this later today. But you can upload this homework from the NLP course from Yandex on Retrieval. So we will use their homework without any changes. Practice. So in this homework, they use dataset, question answering dataset, and we will train our retriever model, and then use this retriever model for the search of the relevant answers. And then use these relevant answers in our generator, which is just a GPT model. So we can start this homework. Let's see. Then you can just watch the video if you're not coding it with me. So collab. GitHub. Runtime, I don't want to use GPU for now. Oh, actually, our small world graph finished running. Okay, let's take a look at the accuracy now. um, oh, and I didn't increase the this heap for construction. Okay. So let's do the search and calculate the approximate. Okay, it's very low. We should reset the search. Oh, it's 45%. It's low. But yeah, to get better accuracy, I also had to reset the heap size for construction because it used 64 neighbors, but then the limit for beam search was smaller. Let's see if we increase the search. Okay, 50%. And for construction, I I'm not sure that it will help. I think this used only during training. Yeah, construction doesn't influence the search. But it's just to give you idea that you can play with different approximate search algorithms. For example, it has also PQ, which is quantized algorithm that will reduce the storage because it will kind of quantize the number of features along the features. If you have 100 features, you can, for example, split them into groups of 5, and the 5 features will be collapsed in one index of the nearest class. So instead of 100 numbers in float, you will have just 20 numbers, integer numbers. Like you can use maybe 2 bits or 8 bits for one number. So it will be more space efficient. Okay, let's go to practice notebook. Load the data. It's not yet. I'm running this now from the there is a link on the Yandex course, NLP course. So I'm running this from this GitHub, but I will upload on our GitHub today. When I will get to Connecticut. So well, yeah, the data will look like this. We have a question and we have different choices of answers, and the label which answer is correct. Let's see, still uploading. Maybe it's no, it's first installing the dependencies. And we will train the model, the retrieval model, that will build the sentence embeddings such that to minimize the distance between correct answer with request with question. It's still up. Okay. Okay. Error. We should import an LTK. Then we need to import data. I will add this in the code, so you don't need to install NLTK. Okay, here's the data set. And the first task is to train the retrieval model. Again, we can use the um, pre-trained model from the box, from sentence transformers. But if you want to make your model more specific for your data, it's a good idea to fine-tune it. So here is just the general pipeline. We upload the model. We create sentence embeddings with torsional graph for several sentences. And then we can look at the similarities. So if we use BERT, you remember for sentence classification, we use Pooler, the embedding of CLS token. We use this. So token embeddings are the embeddings of all tokens, and Pooler is the, well, I'm not quite correct. Pooler, it's a linear lay applied to embedding of CLS token. So we can build the similarity between phrases, and you can see which phrases are more similar. How old are you, and what is your age? So the first and the upper last are the most similar, and in the similarity we can see the upper last and the first, they have higher similarity. So we want to create the model that returns embeddings for questions and answers. And we have kind of correct and incorrect answers. So the first function, vectorizer, we will use the pre-trained BERT model and apply a head to the head of, because our CLS token has a head, and this head is called Pooler, but we will also, in the simplest setup, add extra two linear layers. So let's create self-sequential and add n dot linear. Oh, it actually understands that the output shape of the BERT model is 7. Because otherwise we had to print the shape of the output out of this pooler. Okay. RLU, linear RLU, okay, it looks good. And I will use just two layers. And in our model, we will just copy paste this code with torsional graph to get embeddings from BERT model. What is that? Del. Oh, it maybe. Then we will do CLS embeddings, apply linear layers, and return embeddings. So what we're doing here, we let's see. The input is input phrases. We apply tokenizer to input phrases. That input phrases. And I think that's fine. Let's test our model. Yeah, so we apply BERT model, we get some embeddings, but after that, we'll pass this embeddings through a very shallow neural network. And these are our embeddings. Maybe it was better to unfreeze the this polar layer and just train this layer. And the next step is to train our retrieval model. Here is the code just which samples triples the query, positive answer and negative answer. So this is just written for us. So this is how this iterate mini batches works. So it returns a question, and this is a batch. This is a batch. How many people protested on the San Francisco Torch Road? I think it's not PyTorch. So then correct answers. Correct answers. These protests, and the wrong answers. The wrong answer is chosen randomly from, you remember in the dataset there are many wrong answers. So for every batch, we choose just one incorrect number. And to create better embeddings, there are different loss functions. One of them is called triplet loss. So this is the illustration. The triplet loss wants to train the classifier with a margin such that incorrect answers are separated from correct answers by a margin. So delta stands for this margin, and this is the triplet loss that we should write. And I don't remember, so I will just ask ChatGPT. To write the code. Okay, it looks correct. And paste. This is how you should do homeworks. So the first function is correct, the dot product. The second function, it creates embeddings. Yeah, it looks correct. And let's try to pass assertions. And the assertions are passed. Good job. Plus 2 points. So, and then there is a function to calculate recall. Again, we can ask ChatGPT to write. So here but actually maybe ChatGPT doesn't know which model we're using, and our model was called vectorizer. Oh, question vectorizer and answer vectorizer. So we will use question vectorizer here for embeddings for questions applied to questions, and question and answer vectorizer for answers. And we have correct answers and we have incorrect answers. Correct answer. answers. And the same for incorrect answers. Incorrect answers. Oh, it's wrong answer. Yeah, but there is another problem that our input should be a list, and output from our batch was array, NumPy array. So let's first correct incorrect answers, correct to wrong answers, and then we also need to cast those into list. How to do that? List to list. To um, list, maybe. Let's see. Huh?
Question.
Um, oh, it looks working now. Okay, so this is the function for recall. Typically in retrieval, we calculate not accuracy but recall because it's unbalanced data. Okay, I think we should stop here. And yeah, you will continue this homework at home. Okay, and yeah, next week we will. I looked at this Flux. It uses the stable diffusion, and I was thinking to talk about large language models for image or video understanding. So I added the list if you want to cover like other topics during remaining 2 weeks, then we can cover generative models because these multimodal large language models, they are kind of they generate text, but they don't generate other modalities. If you want to generate other modalities, you need to use the generator for images. Okay, let's stop.